Okay, so now I'm gonna speak about a very particular kind of Laurent series. And in this video, what we're going to do, we're going to play around. We're going to take the geometric series, and we're going to see how we can manipulate a geometric series to derive all sorts of Laurent series. And the examples which I'm about to do in this video, uh, you get a lot of questions like this actually, very classic Laurent series questions. So this one's very important. So what's the basis for all this? Well, you should all know the geometric series of 1 over 1 minus z. Okay, this says Taylor series expansion sum from n equals 0 to infinity of z to the power of n. And recall that this is valid if modulus of z is less than 1, right? So we know this one. From this, we can actually derive another important geometric series. How do we do that? Note that if you have 1 over 1 minus z, then you can write this as 1 over z times 1 on z minus 1. Which can also be written as minus 1 on z times 1 minus 1 on z. Okay, so now what do I notice? I notice that this is exactly what I have. This is exactly what I have here, right? But now z has been replaced with 1 on z. That's the only difference. So according to the formula I have up here, this can be written as minus 1 on z times the sum from n equals 0 to infinity of 1 on z to the power of n. But this is provided, see, before the modulus of z was less than 1, but now we're replacing z with 1 on z. So this is provided the modulus of 1 on z is less than 1. Okay, and this can be written as minus sum from infinity n equals 0, 1 over z to the power of n plus 1, provided, now to say the modulus of 1 on z is less than 1, that's the same as saying the modulus of z is greater than 1. So, what have I done actually? I've derived a Laurent series for 1 on z in two separate regions. So what I found is that 1 over 1 minus z, it can be written in two different ways depending on which region you would like for it to converge. If you wanted to converge when the modulus of z is less than 1, so in other words inside the unit circle, you can write it in this way. Okay, so this is the fact that we started with. Or if you wanted to converge outside the unit circle, you can write it as, and I think it's better actually if I start from n equals 1. So I can write this as 1 over z to the n instead of z to the power of n plus 1. And this will converge when the modulus of z is greater than 1. So this is actually the main result for this video. I mean, it may look simple, but this is the result which we're going to use over and over. So it might be an idea for you to pause this video actually, jot down this result, because I'm about to use it in all the examples that follow. So let me move on. So let's have a look at an example. So what I'm going to do, I'm going to find the Laurent series of f of z equals 1 over z minus 4, that is valid. Oops, sorry about that. That is valid. And I'm going to consider two different regions. In part A, I'm going to consider the region when modulus of z is less than 4. In part B, I'm going to consider the region when modulus of z is greater than 4. Okay. So let's see how we would do this using the results I derived. Okay, well, for part A, I need modulus of z to be less than 4, right? And this can be equivalently written as modulus of z on 4 should be less than 1. In part B, I need modulus of z to be greater than 4. Or in other words, modulus of z over 4 to be greater than 1. Why have I written it like this? Because now I can see, if I call this result that I found earlier, if I call it asterisk, I can see that if I replace z with z on 4 in asterisk, then I can find the Laurent series I want, right? If I replace z with, replace z with z on 4 in asterisk, then what do I get? I get 1 on 1 minus z on 4. Okay. Now in the top case, if I replace z with z on 4, that just becomes z on 4 to the power of n, where modulus of z on 4 is less than 1. I remember, like I said earlier, that just means modulus of z is less than 4. And in the bottom component, if I replace z with z minus 4, this becomes 1 on z on 4 to the power of n, provided modulus of z on 4 is greater than 1. Or in other words, modulus of z is greater than 4. Right? So, and if you think about it, the function f of z, which is 1 on z minus 4, well, this can be written as, if I take out a factor of a quarter, this can be written as z on 4 minus 1 on the denominator. So if I take out another factor of negative 1, so negative quarter, then this will become 1 minus z on 4. And as you can see, I already have the power series expansion for 1 over 1 minus z on 4. So this one is just going to equal two cases, right? Sum from, so it's going to be negative a quarter, infinity, n equals 0. So z on 4 to the power of n, I can just write that as z to the power of n on 4 to the power of n. And as we said, this is when the modulus of z is less than 4. And if I multiply the bottom component by negative a quarter, I get positive a quarter, sum from n equals 1 to infinity. Now z on 4 to the power of n, if I do 1 over that, that's going to become 4 on n to z to the power of n. And this is valid when modulus of z is greater than 4. And that's it, actually, I'm finished. So this is my answer to part A, and this one's my answer to part B, right? So that's how you can manipulate a geometric series to find a Laurent series for this sort of function, right? Um, yeah, that's pretty much it for that example. Let me have a look at another example. Let's have a look. So example, now I'm going to find the Laurent series for, let's see, I think a good one to do would be f of z equals 1 on z plus 7. And I want to find Laurent series that are valid. In part A, I'll take modulus of z to be less than 7. In part B, I'll take modulus of z to be greater than 7. Of course, z itself can't equal modulus of z can't equal 7, right? Because I know that z is undefined at -7 because the denominator is 0. So it's either when the modulus is less than 7 or greater than 7. Okay, and so this one I'm going to use a similar technique to the previous example. So what I'm going to say is note that modulus of z is less than 7. That's the same as saying modulus of z on 7 is less than 1. And to say that the modulus of z is greater than 7, that's the same as saying modulus of z minus 7 is greater than 1. So, you may be thinking, well, this is pretty much what we had before. Let's take that result that I had, the one I called asterisk, right? And let's replace z with z on 7. That won't actually work. The reason it worked last time, because I had z minus 4 on the denominator. But now I don't have a minus on the denominator. I have z plus 7. And the trick in this case, instead of replacing z with z minus 7, the trick is to actually replace z with minus z on 7. Okay, so if I replace z with minus z on 7, if I replace z with minus z on 7 in asterisks, I hope you've jotted down that result, because like I said, I'm going to use it a fair bit. But if I replace z with minus z on 7, then that result that I had before becomes 1 minus z on 7. Now in the top case, it's going to become sum from n equals 0 to infinity of minus z on 7 to the power of n. And this is provided modulus of negative z on 7 is less than 1. As you can see, the negative sort of has no effect in the modulus part, because we're taking the modulus, the negative will go away anyway. So this is still going to be equivalent to modulus of z is less than 7, which is what I want. So that's why the trick works. And the bottom part is going to become negative sum from n equals 1 to infinity of 1 over negative z on 7 to the power of n, where modulus of negative z on 7 is greater than 1, or in other words, modulus of z is greater than 7. So the top half will give me the series I need for part A. The bottom half will give me the series I'm after in part B. Okay, so now what I have to do, I have to take f, which is 1 on z plus 7, and somehow rewrite it or rearrange it, write it in terms of this guy here, 1 over 1 minus z on 7. And the way to do that is fairly simple. Note that 1 over z plus 7 Again, if I take a factor of 7 out on the denominator, this becomes z on 7 plus 1. And of course, this can just be written as 1 on 7 times 1 minus z on 7. Yeah, because a negative and a negative makes a positive. So all I have to do, I just have to rewrite the expression from before and put a 1 on 7 out the front. So it follows that f of z, if I put a 1 on 7 out the front on the top, then I get this. So now I have negative z on 7 to the power of n, so that's going to be negative 1 to the n on 7 to the n, z to the n, which converges in this region. And on the bottom, if I put a 1 on 7 out the front, I get negative 1 on 7, sum from n equals 1 to infinity, and this guy is going to be the reciprocal of the other guy, so it's just going to be negative 1 to the n, 7 to the n over z to the n. And this will converge when modulus of z is greater than 7. So that's it. Those are my two Laurent series. So this guy here converges when modulus of z is less than 7, which is what I wanted for part A. And to get a Laurent series which converges when the modulus of z is greater than 7, just take this guy. So that's how you do it. That's how you find the Laurent series for when you have a positive on the denominator. Okay, so those two examples which I just did, not too difficult because there was only one singularity. So only one point where the function f was undefined. I mean, in the case of 1 over z minus 4, it was only undefined at z equals 4. And in the case of 1 over z plus 7, it was only undefined when z equals negative 7. Now what I'm going to do, I'm going to consider a function which has singularities at more than one point. And this one's not that hard either, actually, but it will just take a little bit more thinking, a little bit more thought than the previous two examples. So let's have a look. What I'm going to do now is I'm going to find the Laurent series of, I'm going to take f of z to be z plus 5 on z squared plus 4z plus 3, and I want to find the Laurent series that converges in the annulus 1 is less than modulus of z, which is less than 3. So in other words, I want z to be between a circle of radius 1 and a circle of radius 3, both centered at the origin. Okay, how do we do this one? Well, first thing, we factorize, we factorize the denominator of z, the denominator of f, which will be z plus 1 over z plus 3. And then actually the key step after this is to decompose f into partial fractions. That's the key. So to write this in the form a on z plus 1 plus b on z plus 3. Okay, why do I do this? Because now, for each of those fractions, I know how to find the Laurent series. It just becomes like the previous two examples, right? So if I can get into partial fractions, it'll be very easy to get the Laurent series for f. I just repeat what I did in the previous examples. first things first though, we need to figure out what A and B are. So let's see, for this to be true, I need z plus 5 to equal A times z plus 3 plus B times z plus 1. If I substitute z equals -3 into that equation, left hand side becomes 2, right hand side becomes -2b, therefore b equals -1. If I substitute z equals -1 into this equation, left hand side becomes 4, right hand side becomes 2a, therefore a is equal to 2. So what that means is that f of z is equal to 2 on z plus 1 minus 1 on z plus 3. Okay, so now let's think about this part carefully. With that first fraction, 2 on z plus 1, I know how to find the Laurent series when the modulus of z is less than 1 and when the modulus of z is greater than 1. Right? Undefined when the modulus of z is equal to 1, obviously. And with the second fraction, again, using the techniques from the previous examples, I know how to find the Laurent series when the modulus of z is less than 3 and when it's greater than 3. But keep in mind, what do I want? We want convergence in this particular region. I want the modulus of z to be between 1 and 3. So what does this mean? On the one hand, I want the modulus of z to be greater than 1. And on the other hand, I want the modulus of z to be less than 3. Now, to say the modulus of z is greater than 1, well, that one's going to be easy, right? This is just equivalent to saying modulus of negative z is greater than 1. Again, why am I replacing z with negative z? Because I have that positive on the denominator, right? That's just like example 2. And to say the modulus of z is less than 3, this is the equivalent of saying modulus of z on 3 is less than 1. But again, I should do negative z on 3 because I have a positive on the denominator. Okay. So I'm going to need that result from before. So just in case you didn't jot it down, I'll just write it out quickly. So recall that 1 on 1 minus z is equal to 2 cases. You can have sum from n equals 0 to infinity of z to the n if modulus of z is less than 1. Should bring this guy down a little actually. It's gonna interfere with the previous. Okay, that's better. Alright, and I know that I can also write it like this. Okay, let me call this series I, and this series I. Okay, so what I'm going to do is I'm going to replace z with minus z in I. Okay, so what is this going to, well actually, is that right? I should replace z with minus z in I, shouldn't I? Because I want the modulus of negative z to be greater than 1, not less than 1. So if I do that, what I'm going to get 1 on 1 minus z equals negative sum from n equals 1 to infinity of 1 over negative z to the n. So in other words, 1 over 1 plus z equals, it's going to be sum from n equals 1 to infinity, and I guess that would be negative 1 to the power of n plus 1 over z to the n. Right? And this is valid when the modulus of negative z is greater than 1, or in other words, when the modulus of z is greater than 1. Right? Next thing that I'm going to do, I'm going to replace z with negative z on 3. In I, right? Because I want modulus of negative z on 3 to be less than 1. So, what do I get there? I'm going to get 1 over 1 minus z on 3 equals sum from infinity n equals 0. Sum, so it's going to be negative z on 3 to the power of n. Okay, so in other words, 1 over 1 plus z on 3 is equal to sum from n equals 0 to infinity, negative 1 to the n on 3 to the n, z to the n. But keep in mind, I want to get a series expansion for 1 on z plus 3. This guy, right? Not really interested in 1 over 1 plus z over 3. So how do I do that? Well, I know that 1 over z plus 3, this can be written as a third times 1 over z on 3 plus 1, right? So all I have to do, I have to stick a third in front of the series I just found. Yeah? So what I get is that therefore 1 on z plus 3 equals sum from infinity n equals 0, negative 1 to the n on 3 to the power of n plus 1, z to the n, and this is valid when modulus of z is less than 3. Right? So now that I have the two individual series, I just subtract them, right? So it follows in the region where modulus of z is between 1 and 3, we have, so remember f of z was equal to 2 on z plus 1 minus 1 on z plus 3. So I know that 1 on z plus 1, I have a expansion for that. I stick a 2 out the front. So it's going to be infinity n equals 1, 2 times negative 1 to the n plus 1 on z to the n. Right? Plus, actually it's going to be minus sum from n equals 0 to infinity of negative 1 to the n on 3 to the n plus 1 z to the n. And that's pretty much it. So that's my Laurent series when the modulus of z is between 1 and 3. Um,